Section 1 Introduction. We're here to discuss a recent development in the field of training models with extremely long maximum sequence lengths. A team led by Liu introduced an efficient algorithm called ring attention. This algorithm allows for the distribution of self-attention computations across multiple devices connected in a ring-like structure. By dividing the queries, keys, and values in each self-attention layer across the memory of multiple accelerators, ring attention enables the training of models on sequences that are much larger than what a single device could handle. Moreover, ring attention is designed to maximize efficiency by overlapping cross-device communication with on-device computation. This results in high throughput and low overhead compared to self-attention implementations that run on a single device. As far as we know, ring attention is currently the most efficient algorithm for exact long-context self-attention. In this paper, we aim to show a simple method to further improve the throughput of ring attention, specifically for causal self-attention. This type of attention is used in generative language models like GPT and Llama. Causal self-attention is known to be more cost-effective than general bidirectional self-attention because each query only interacts with keys that appear earlier in the sequence. This reduces the total number of operations required by roughly half. In a single device setting, optimized kernels like flash attention already take advantage of this characteristic of causal attention to significantly increase throughput. However, we've noticed that ring attention can't effectively use the structure of causal attention to improve its throughput on a per-device basis. This is due to a workload imbalance. In all but the first iteration of the ring attention algorithm, some devices' workloads are entirely necessary, while others are entirely unnecessary for the final output. The speed of ring attention is determined by the maximum latency of any participating device per iteration. As a result, regardless of per-device optimizations, the latency per iteration would be the same as the time taken to compute a fully unmasked workload. This means that ring attention will run as fast as a workload with no attention masking, despite theoretically needing to compute only half the operations. To effectively use the structure of causal self-attention, we need to change how ring attention divides work among devices. We propose striped attention, a variant of ring attention that rearranges the input sequence in a way that almost entirely eliminates the workload imbalance present in the original ring attention algorithm. In particular, we rearrange the sequence so that every device always operates on a non-continuous subset of tokens distributed approximately uniformly throughout the original sequence. This ensures that about half of the query-key interactions on each device will be inhibited by the causal mask. Like ring attention, striped attention is an exact attention algorithm. We exploit the permutation equivariance of the core attention computation to ensure that our decision to internally rearrange the input sequence does not affect the final output of the model. Unlike ring attention, striped attention can take advantage of the structure of causal attention to save time on every iteration. Using an implementation of striped attention built as an extension to Liu et al.'s ring attention codebase in JAX, we observed end-to-end speedups of up to 1.45 times when training billion-scale causal language models on sequences with hundreds of thousands of tokens using a server with 8 180 GB GPS. We saw even greater speedups on TPUs, achieving 1.65 times speedups on problems with over 500,000 tokens on 16 TPU v4 chips. We're releasing the code for our experiments as open source. We hope that striped attention can serve as a foundational technique to enable researchers to explore new applications in the emerging domain of extremely long context causal models. In summary, this paper contributes the following. 1. We identify a workload imbalance in ring attention which prevents it from taking advantage of the structure of causal attention to save computational work. 2. We propose striped attention, a modification to ring attention which resolves this workload imbalance to improve throughput on causal sequence modeling tasks. 3. We experimentally measure the throughput of causal training with striped attention, and find that our implementation enables up to 1.65 times end-to-end speedups over the original ring attention algorithm when training with long sequence lengths. Next, we'll delve into the background of causal self-attention. The main goal of this paper is to define an efficient distributed implementation of the core causal self-attention operation in the architecture. Causal self-attention takes as input matrices Q, K, and V, where N is the input sequence length and D is a hyperparameter. It computes a function called causal add of Q, K, and V, which involves a softmax operation and a causal mask matrix C. The elements above the diagonal of C are negative infinity, with zeros elsewhere. Adding negative infinity to an entry of the matrix QK, transposed, removes it from consideration in the softmax operation, ensuring that the output of the softmax for that entry will be 0. The causal mask can therefore be interpreted as ensuring that the output row of attention at a given position in the sequence will be affected only by rows of the K and V matrices occurring at equal or earlier positions in the sequence. Upon inspecting the structure of the causal self-attention operation, we find two opportunities for saving work in an optimized implementation. 1. We can avoid computing approximately half the elements of the product QK, transposed, namely, those above the diagonal, which will all be set to negative infinity by C2. We can avoid multiplying V by approximately half the entries of softmax, QK, transposed, plus C, namely, those above the diagonal, which are all guaranteed to be 0. These optimizations are well known and are utilized in fused implementations of attention like flash attention, which avoid materializing the full softmax, QK, transposed, plus C, matrix in global memory. Under ideal conditions, these optimizations can deliver up to a 2 times reduction in the number of flops required to compute causal attention. In reality, hardware limitations and fixed overheads reduce this factor. Section Summary. In pursuit of training models with long sequence lengths, Liu et al. Proposed ring attention, an algorithm that distributes self-attention computations across multiple devices. However, ring attention cannot effectively exploit the structure of causal self-attention, resulting in a workload imbalance. To address this, we propose striped attention, a modification to ring attention that eliminates the workload imbalance and improves throughput on causal sequence modeling tasks. Our experiments show that striped attention achieves up to 1.65 times speedups over the original ring attention algorithm when training with long sequence lengths. Section 2.2 Ring attention. The recently introduced ring attention algorithm offers a method for spreading the attention computation across multiple processing units, like GPUs or TPUs, that are connected in a ring communication structure. If we have n devices available, ring attention assumes that the matrices Q, K, and V are initially divided across the sequence dimension, breaking them down into equal-sized blocks of rows. To put it simply, imagine that we have these matrices divided into blocks, with each device initially holding a set of blocks. For instance, device 0 holds the blocks Q0, K0, V0, device 1 holds Q1, K1, V1, and so on. The ring attention algorithm then calculates the output of attention by performing n rounds of computation and communication. It keeps the Q blocks stationary on their respective devices while passing the K and V blocks from one device to another in a circular manner. On each round, each device calculates the interactions between the Q block it owns and the K and V blocks it currently holds. Each device has a stationary block of rows of the output matrix that corresponds to the same sequence positions as its Q block. Devices accumulate partial outputs across rounds using a strategy called the lazy softmax strategy. A noteworthy function in this algorithm is the getMask function, which returns a part of the attention mask that governs the interaction between the query block Qj and the key value blocks Kk, Vk. When using ring attention to compute causal self-attention, the output of getMask is determined as follows. If j is less than k, then all values in the mask are set to negative infinity. If j equals k, then for all x, y where y is less than x, the mask values are set to negative infinity. If we think of the original causal mask C as an n by n matrix of blocks, each of shape n_seq, n by n_seq, n, this logic for getMask is equivalent to selecting the entry at position j, k and c. However, there are some limitations. On all but the first round, workload imbalances prevent us from effectively using the structure of the causal mask to reduce runtime. Even though some devices' interactions are entirely masked out, we cannot save any time by having these devices skip their computations because other devices' interactions are entirely unmasked. To make computations more efficient, blocks are further divided into tiles. For each tile, we check if it is entirely masked out. If so, we skip computing the tile entirely. For example, if we had a tile size of 512 by 512, and a block size of 9 tiles, or 1536 by 1536, then in the case of a block with casual masking 3 tiles would be fully unmasked, 3 tiles would be partially masked, and 3 tiles would be fully unmasked. We would avoid computing the last 3 tiles, resulting in a 33% reduction in compute. Striped attention is a novel approach that reduces the workload imbalance in ring attention for Causal S by partitioning the sequence in a new way. Instead of partitioning the tokens into contiguous blocks, we partition them into sets of evenly spaced stripes based on their residues modulo the device count n. For example, given a device count of 4, device 0 would own tokens 0, 4, 8, and so on. Device 1 would own tokens 1, 5, 9, and so on. In practice, we can achieve this partitioning scheme by permuting the input tokens before the model's first embedding layer, and then partitioning the permuted sequence into contiguous blocks as in ring attention. After partitioning, our algorithm proceeds almost identically to ring attention. At the beginning of each attention layer, each device I initially holds blocks chi, key, v, which inherit the striping permutation applied to the original input sequence. On each round of the striped attention algorithm, each device I computes causal attention interactions between its assigned chi block and the k, v blocks that it received in the previous round. The attention computation in striped attention is causal with respect to the order in which tokens appear in the original input sequence, not their order in the permuted sequence. This has important implications for the structure of the mask returned by getMask. In contrast to ring attention, striped attention ensures that every device's causal mask is upper triangular on every round. When computing causal blockwise attention between block chi and blocks kj, vj, striped attention yields a per-device workload of c plus 1, 2 attention interactions if I is greater than or equal to j, and c1, 2 attention interactions if I is less than j, where c is the per-device block size. In comparison, ring attention's computation schedule has at least one device on each round which must process a workload of size c squared, which acts as the limiting factor on the latency of each round. As the block size grows, the fraction of the attention matrix taken up by the diagonal shrinks linearly, and the workload imbalance becomes negligible as a fraction of the total runtime. In the limit as block size and device count go to infinity, the maximum theoretical speedup from using striped attention over ring attention approaches 2 times. Section Summary. The ring attention algorithm distributes attention computation across multiple accelerators connected in a ring communication topology. It partitions the matrices Q, K, and V into blocks and computes the output of attention through multiple rounds of computation and communication. The striped attention algorithm further divides the blocks into tiles and partitions the tokens into sets of evenly spaced stripes, reducing workload imbalance and ensuring that every device's causal mask is upper triangular on every iteration. Section 3.1 Implementation. We've extended the ring attention codebase developed by Lou and his team to include our striped attention model. We then compared the performance of both models using several billion parameter scale causal training benchmarks. We conducted our experiments on 3 different configurations. 1. A server equipped with 8 NVIDIA A180GB GPUs linked via NVLink. 2. A TPU pod slice with 4 TPU v3 chips, or 8 tensor cores. 3. A TPU pod slice with 16 TPU v4 chips, or 32 tensor cores. Both the ring attention and striped attention models use a method called coarse-grained tiling to avoid unnecessary computations. This involves breaking down the space of query-key interactions into smaller sections, or tiles. The size of these tiles varied between our GPU and TPU experiments. We found that the best performing tile sizes for ring attention also worked best for striped attention. For the A180GB GPUs, we used a tile size of 2048 queries by 4096 keys. For both V3 and V4 TPUs, the tile size was 2048 queries by 2048 keys. We then calculated the attention interactions for each tile, but only if it contained at least one unmasked element. This technique of skipping work only provides a performance benefit in the first round for ring attention, but for striped attention, it can provide a benefit in every round. We performed all computations in bfloat16 format, except for the core attention computation, where we used float32 buffers. On NVIDIA A100 GPUs, the matrix multiplications for attention were performed in NVIDIA TENSORFLOAT32 precision. On TPUs, these operations were performed in bfloat16 precision. We explored the effect of varying 3 aspects of the training configuration on the relative throughput of striped attention to ring attention across devices. 1. Model size. We tested 1B, 3B, and 7B model configurations. 2. Sequence length. We tested training with total cross-device sequence lengths ranging from 8,192 to 262,144. 3. Distributed mesh dimensions. We tested degrees of sequence parallelism ranging from 2 to 8 devices, and varying degrees of model parallelism between 1 and 4. Our results showed that striped attention consistently outperformed ring attention in terms of training speed. This was particularly noticeable at a sequence length of 256K. We also found that the benefit of our method scales with sequence length in multiple ways. In theory, striped attention can reduce the runtime required by the core attention computation in ring attention by up to a factor of 2. However, there are other costs that contribute to runtime, and striped attention only speeds up the final N1 iterations of ring attention. We found that there is a gap between the speedup achieved by our implementation of striped attention and the theoretical maximum speedup. This gap narrows as sequence length increases. We attribute this gap to two main factors. First, our implementation skips work at the granularity of tiles, which means that at small per-device block sizes, we are not able to take full advantage of the causal mask to skip half the work in attention. Second, we suspect that non-attention computation overheads in both the ring attention and striped attention implementations we use for our experiments reduce the speedup achievable by striped attention. We look forward to future implementations of striped attention which employ fused kernels like flash attention, which we expect will make it possible to achieve greater speedups at smaller block sizes by skipping work at a finer granularity. We also believe that improved overlapping of computation and communication may increase the observed speedup. We leave the development of more carefully optimized ring attention and striped attention implementations to future work. Section Summary. The authors implemented striped attention as an extension to an existing codebase and compared its performance to ring attention on large-scale training benchmarks. They used different hardware configurations and tile sizes for the attention computation. The results showed that striped attention achieved speedups that scaled with sequence length and block size, but there was still a gap between the achieved speedup and the theoretical maximum speedup. This could be due to the granularity of work skipping and non-attention computation overheads. Future work could explore finer-grained work skipping and optimized implementations of both attention methods. Section 5.1 Distributed Execution in Deep Learning. In Section 5.1, we discuss the evolution of distributed execution in deep learning. As the complexity and computational demands of models have increased, new strategies for parallelism have been developed. One of the earliest examples of this was the use of data parallelism through a parameter server for deep learning. Another approach, known as model parallelism or specifically tensor parallelism, has been in use since the development of AlexNet. It gained popularity for training large language models with improved implementations like Megatron LM. These implementations were able to scale better with tensor parallelism than previous data parallel approaches. As the memory requirements for training large language models increased along with the batch sizes used during training, gradient accumulation became a popular technique. This led to the development of efficient pipeline parallelism methods such as gpipe. Although gpipe was less computationally efficient than previous methods, it saved on memory and communication. Another method, fully sharded data parallelism, achieved the memory savings of tensor and pipeline parallelism by sharding the parameters instead of communicating activations. In relation to our work, sequence parallelism was introduced, which is a type of parallelism specifically designed for long sequence length attention. An efficient combination of tensor and sequence parallelization was proposed, further adapting Megatron LM to very long sequence lengths. In Section 5.2, we discuss efficient attention implementations. While the feed-forward layers of models can easily achieve high utilization on modern accelerators, attention has historically had lower device efficiency. Many approaches have been tried to address this issue. One common approach is the introduction of computational approximations of attention. While some methods like linformer and the sparse transformer attempted to approximate the computation of attention with linear and sparse equivalents, these methods never gained the popularity of the original attention implementation. A memory-efficient algorithm for self-attention was proposed that reduced the memory requirement from a quadratic relationship with the input size, O, n squared, to a constant 1, O, 1. A practical implementation of this algorithm that required memory proportional to the square root of the input size, O, sqrt, n, was also proposed. Flash attention provided an efficient implementation of this algorithm that leveraged custom CUDA kernels and several optimizations accounting for the GPU memory hierarchy. Flash attention 2 further optimized the parallelization of computations across the GPU process hierarchy, better dividing work between and within thread blocks. In section 5.3, we discuss system optimizations for very long sequence lengths. Recent work has explored other efficient distributed attention approaches for long sequence lengths. DeepSpeed Ulysses focuses on improving the communication efficiency of sequence parallel models by replacing all gather and reduce scatter operations with smaller all-to-all operations. LightSeek also optimizes the communication operators for sequence parallel models. In addition, they also add an improved rematerialization strategy and enable the overlapping of communication and computation by splitting the workload into bubbles. However, while ring and striped attention keep the queries fixed while enabling the overlapping of communication and computation, the overlapping of LightSeek requires moving both the queries and the keys.